Hello there, this is Sohail Hasni, your host at Energypreneurs. Cheap solar power, batteries, and electric vehicles are changing the transport and energy sector as we know. I bring in guests to this podcast who will help you with their ideas to navigate this energy transition. Thank you for joining. The food that we eat, the waste that we generate, it has a lot of values for fertilizer, for electricity, and this can be recycled quite nicely. So here is a conversation with David Ellis, who will take us through this journey, how the technologies can be used for a large scale and small scale systems to take our waste, not ending up in a landfill somewhere, but again, be part of the bigger ecosystem. Morning, David from Manila.
Good morning, Sohail. I'm from Toronto, Canada.
Let's introduce yourself and get into this conversation. I'm very excited about this topic, something I have not with someone yet.
Well, thank you so much. So my topic is anaerobic digestion of organic waste. My background is in chemical engineering. My name is David Ellis, and I'm the founder here at Azura Associates. So we're a niche process engineering company. Anaerobic digestion is the only potentially carbon negative fuel in the world. It is the only one in the world that's potentially carbon negative. And it's because we're able to take food waste and other organic wastes and harvest the energy that comes from that. Anaerobic digestion in general, it's not a new thing. It's a natural process. It occurs in the muck in the bottom of lakes and rivers all around the world. It's being harvested or industrialized or engineered for more than 100 years in warm climates in places like India, for instance. Been using digesters for more than 100 years around animal manure and human manure. The civil engineering world, about 50 years ago, discovered this as a way to help kill pathogens that were in human sewage sludge from sewage treatment plants. Using engineering principles, we can concentrate that into a tank. We can intensify it. We can make it into a small, fast, controlled process instead of something that just occurs naturally in the bottom of lakes and rivers. If some debris sinks to the bottom of a river or a lake and into the mud, it might biodegrade anaerobically in nature. But in an anaerobic digester, we can do that in a controlled way. And instead of having that methane that would be produced in the soil or in the mud at the bottom of a lake or a river, there it would bubble up to the top of the surface of the water and be released to the atmosphere. Now, the thing about anaerobic digestion is it does produce methane. And methane is a very potent greenhouse gas. It's 84 times more powerful than carbon dioxide. So it is much, much worse.
Well, we are using about 22, so things must have changed.
So that has to be a 20-year time horizon. When we look at the half-life of methane in the atmosphere, on the order of 7.5 years. So when we look over a 20-year time span, it's actually much more than the 22, 24. I've seen 28 published as well over different time spans. So the 84 is based on a 20-year time span.
Okay, so with this technology, what could be a typical $10 million project?
Oh, a typical $10 million project would be a large dairy farm or a large farm that has livestock, plus a portion of food waste from a local apple pie factory, food manufacturing facility, ice cream, cheese plant, or from source separated organics, municipal waste. Everyone has a little bin on their kitchen counter, banana peels, onion skins, and different material goes in there. A $10 million project is a pretty good sized digester project. A simple on-farm system, about 50% manure and about 50% food waste. It depends if the government's involved. But if it's just a private sector job, we could be looking at 20 to 30,000 tons per year of food waste plus manure going to that size of facility. That'd be a very good size digestion application.
How many hectare will it need, the facility?
Oh, the facilities are relatively small.
Should be small.
Acres to hectares. A lot of the farmers in this area still use acres, but I would expect we'd be looking at a handful of hectares involved, really, because the anaerobic digester is an intense process that happens inside tanks, much say a greenhouse would be for farming. So the physical plot size would be 1 or 2 hectares for this size facility.
And then you need to have a system to collect all the food waste from different places, including used oil from fries and restaurants. Can that be as well?
Yeah, absolutely. So the used oil from French fries and restaurants are a great fuel source. High calories means high gas potential.
So get collected, and you need electricity or some form of energy to trigger the process.
The process can be self-sustaining pretty easily once it gets going. But yes, to initiate it, you need electricity to pump and make mixers turn and operate the mechanical equipment. Biology likes a nice warm temperature, 38 degrees Celsius. So if you're trying to start a process in a cool season, you need to add some heat to warm it up. And once the biology wakes up and those bacteria spring into action, they start producing methane, and then it is a energy positive undertaking.
Yeah. So then you have to collect the methane, use it somewhere else, like a biogas equivalent. I think a lot of places in Asia, it's very common. People collect the cow dung and then the burns. It's a similar process, but you're doing in a large scale, right?
Correct. On a small scale, one family, a small farm in parts of Asia, we may collect the dung, collect enough gas over the day to cook the dinner. The facilities are commercial and industrial scale, where you're talking several hundred or several thousand milking cattle of dairy cattle, or all of the food waste collected in a mid-sized community, say 500,000 people. And those industrial applications collect significant biogas, the biomethane. You can burn that in an engine to make electricity, or purify it to refine biomethane or renewable natural gas to use in the distribution network. And that's done more and more in this area where it's injected into the gas grid. In Canada, we have plentiful natural gas from oil deposits and a long-standing gas grid across the country and into the United States. We have gas storage in Ontario. We can store an entire winter's supply of natural gas in underground salt cavern. If there's any disruption of the pipeline, it actually doesn't matter for 6 months. We can run all winter long with just what is stored before the pipelines to Alberta are repaired.
Yeah, that reminds me, mid-90s, there was a big disaster in Langford in Victoria, Melbourne, where we didn't have gas for more than a couple of weeks. The whole state was shut down. I had an all electric home. Friends were coming for hot showers and dinner. Yeah, I think it happened in Langford in Victoria, mid-90s.
Yes.
This is one of the largest gas disasters.
Wow.
So these systems, 10 million looks like a large project for a large farm, especially maybe government involved, because you have to ensure there's sufficient feedstock, all sorts of other risk, right? But there could be at the other end, very small, efficient one, few families.
What we're seeing now is that the cost of some of the specialized purification equipment can be quite expensive. So in terms of economies of scale, renewable natural gas, the gas upgrading equipment, I would call it, the biogas as it's produced in the reactor tanks is about 50% carbon dioxide, about 50% methane, maybe 60% methane, maybe a little more, but in that range. That needs to be refined before that can be used in a natural gas grid. That upgrading equipment is quite expensive. We are only seeing that being used on large projects, millions of dollars, 5, 10, 20 million. For example, in 2008, the city of Toronto embarked on a large digester project that was $75 million, 75,000 tons per year, food waste from the people in the city of Toronto. We are seeing more projects in the hundreds of millions of dollars, so $200 million or more, to deal with food waste from major cities across North America. These projects with a tremendous economy of scale are using upgrading equipment to put the gas that's produced into the national distribution network. On a much smaller scale, 1 or 2 families would only inflate a small bladder. Those are very low cost. They don't have the detailed engineering a large system would have. They tend to be much more simple and easy to operate.
Yeah, because while you are looking at a carbon liability perspective, all this food getting wasted and others, of course, we can capture it, avoid emissions. And as you said, that's a negative emissions in a way, right? You get more than.
Yeah.
But people who do not have remote rural areas of Africa or many parts of Asia, so this could be a livelihood issues, right? Because you can cook food with whatever you.
Yes. I was in Africa this past summer, and one of the conversations I had was around the use of anaerobic digesters for dairy farming to improve the lifestyle and income of dairy farmers. These are small farmers where the milk would be collected in small cars or motorbikes. One of the challenges is when that milk is brought to the central processing facility, if the electricity is off, they're not able to run the chillers rapidly to cool the milk and to have it stored. It's not a question of energy cost, it's a question of energy security. The concept was that if the farmers could make their own digester, they can store their own biogas and run the biogas through their engine to make electricity to power the chillers. And when that cooling process is done, they can stop that system and allow the biogas to slowly fill up over the night. And they can burn that down for 4, 6, or 8 hours during the day when they need that, and not rely on a local or national grid.
Interesting. I'm just thinking this system will have a very long life, right? Unlike batteries, because you're not buying anything from anywhere.
Right.
It would be simple technology because you're just storing gas and burning it, but you still need a tiny gen set, like a diesel sort of gen set, right?
So it would be fired from the biogas itself. The gen set is an internal combustion engine, 1/3 electricity, 2/3 still wasted as heat, but you're able to get that electricity when you need it, all under your own control. So you're self-reliant. Those who are remotely located, not connected to a national grid, so they like this. You don't need to run 10 or 15 kilometers of high voltage mains. Well, you could make yourself off grid, your own little electrical grid island where you provide the feedstock, produce them, store the gas, and when you need it, turn on your generators and make your own electricity.
Yeah. Now your competition will be solar. You can get a cooling system in a 20-feet container with solar and batteries. So that's essentially your competition. So how does the price stack up? If you want to do a small system, say equivalent of a 10 kilowatt solar, you can set up everything in a $20,000. So what will $20,000 buy?
Oh, good question. I don't know exactly for that size of system, but let me think about that for a moment. There are what the industry term pocket digesters, a shipping container, which has in it a plastic bladder bag that would be constructed. So concrete base with wall panels, a waterproof plastic liner, and a dome lid on top. That's your digester. And there's a mechanical container that goes with that. Those are not $20,000. Those are, I think, quite a bit more than that. That would be over $100,000 for that type of system. There's one I can think of in my area here in Ontario. I wasn't involved with the project, but I believe it's more than $100,000. And I think the number 25 kilowatt generator is the size that comes to mind. I have to check those details to be sure. So solar and battery that may well be preferred if the sun is free, which is fabulous. The connection and the batteries, absolutely, right? Those are excellent opportunities. The dung if the farmer has that for free. So the inputs are free, but the capital of the system is not free. On the storage side, we have batteries as one storage mechanism and the methane as a chemical battery waiting for us to burn it in the engine or to use it in some other fashion. We have seen some projects in Central America where the competitor was not solar, but diesel. Facilities were running diesel-powered generators to help power part of a slaughterhouse, for instance. And in that case, when they're looking at expensive diesel electricity, the biogas system made a lot of sense for sure.
Diesel cannot compete. It must have been at least 5 years back, because now the solar is so cheap and batteries so cheap, relatively speaking. Diesel will be upwards of 25 to 40 cents a kilowatt hour if you take the inventory cost, whereas solar straight maybe 5 cents. If you add battery, maybe another few cents. So no competition there. Solar will be plug and play. Batteries will be plug and play, right? Doesn't work. Pick it up, get another one, plunk it in, right?
Yeah, absolutely. So the food waste, the manure, the dung, all these things to make methane, as long as people eat bananas, we're going to have banana peels. And so there will be that waste disposal issue. But certainly the truth here is as much a waste management tool as it is energy production. The energy piece is the nice cherry on the top. Keeping the waste out of landfills is definitely a key factor. On the energy side, like you said, 5, 10, 15 cents per kilowatt hour here. That's what we pay in this part of Canada. At the same time, we have a tipping fee, a gate fee to take the waste to the landfill. So per ton of material, round number, about $100 per ton of tipping fee. So now the digester operator, they have two pieces to the business model. They have a tipping fee side for the business, and they have an electrical or energy sales side to the business. So they have those two. And then there's the third leg of the stool, which is the digestate. The phosphorus that we use as fertilizer in farming. Phosphorus comes from rocks. It comes from mining. We mine phosphate rock. Potassium, so mining of potash. And ammonia. Ammonia is primarily produced from natural gas. All of those nutrients, the nitrogen, the phosphorus, and the potassium, those are all conserved. Those are all present in the digestate. So this banana peel goes into the digester. It liberates a bunch of energy, and every kilo of nitrogen and phosphorus and potassium that was in that banana peel is still there. It's still in the digestate, ready to be applied back onto farmland to be grown into next year's crops.
So you can take the NPKs out and make a fertilizer, and you can burn the remaining part anyway, right?
That's right. Yes. So the NPK is part of the valuation of the end digestate. And so there's several different ways to handle that. Some folks are looking at, do we produce a dry material, which is typically very rich in phosphorus, or do we take the whole digestate just as it comes out of a wet digester? So this black, mucky material, this kind of stewy mixture, do we take that and apply it on the fields just as the farmers would apply manure? All the NPKs are still there. And also the organic matter. So the cellulose and the other things can help improve the quality of soil. Quite a bit of work is being done by people smarter than me, looking at soil health, soil biodiversity, looking at all the little insects and creatures in soil. Chemical fertilizer soil produce lots of crops, but the digestate fertilized soil has greater markers of biological health and diversity of the microbiome that lives in that soil after the digestate is applied. So definitely improving soil quality as a way to deal with things like helping to mitigate drought, for instance. So a chemical fertilizer does not do all of the same things that the same amount of NPK in a digestate form does.
Again, this NPK is organic, so you can also feed it to all the hydroponic farmers because they're all using chemical NPKs.
Correct. So in My area here, there are several digestates which have been certified for use as inputs to organic farming. So organic certified farms are able to use digestates from certain facilities. Now, those facilities have to be careful a little bit of what they take in. So certainly if people have on their curbside organics, plastics in their waste, eggshells, other things that maybe shouldn't be there, then they have to go somewhere. So either the digester system has some equipment to take that out, or sometimes it can actually go through the system and small little tiny pieces of plastic can end up on the fields. And so that's a problem for sure. All of the farmers that we work with and talk with think about these kinds of things. The farmers understand stewardship, we'll say, so much better than all the MBA that I've met in my life. When I talk to a farmer who is the fourth or fifth or sixth generation of family on the same land, in many places of the world, it goes back, in Canada's a pretty young place, certainly in terms of the European involvement here, that farming system, they take stewardship so much differently. My father, my grandfather, my great-grandfather plowed this land before me. And if I'm lucky, my kids and grandkids and grandchildren will plow it in the years to come. So I am just a steward of this property and this land for a period of time. Nobody wants to be the one who screws it up and has all little bits of plastic and contamination on the farm for the next 500 years. One of the things that I've seen in discussions about anaerobic digestion and food waste is, can it go wrong? And the answer is, of course it can. The technology is well established. My old boss, who's retired now, he was involved in some of the first farm digesters here more than 40 years ago in the early 1980s. Oil price did not skyrocket in those days as people were expecting. Oil did not go to $200 a barrel. Learned a lot about corrosion of the engines from some of the chemicals in the food waste. The sulfur compounds, for instance, cause a lot of corrosion. You know, those lessons have been learned. We understand much better about plastics, corrosion, the technical issues. So really, we're in a very good position overall, but certainly it can be done well and it can be done badly. Unfortunately, we've seen both instances in North America. So right now, I think the key lessons have been learned over the last 30, 40 years. And now the systems we're involved with are much, much better than those earlier operations.
Absolutely. So I think I was asking the wrong question or thinking in a different way. The electricity generation is a byproduct, but your core is that we are all generating all this waste. How do we minimize that waste going to the landfill? How can we bring it back to the part of our everyday living ecosystem? And it's better to be done at the residential level, more of a community or a city level, so that you get all the economies of scale and everything else. Also, it provides continuity of feedstock.
Absolutely. One of the things we look at when we're looking at risk assessments for developers is exactly that. There's a small number of pillars we need to have a great project. One is we have to have reliable feedstock supply, not just 2 years or 3 years, but if we need to guarantee the investment for a 20-year payback period, we need to have a pretty good idea we're going to have 20 years worth of feedstock. So that municipal supply is the most guaranteed supply that there is, right? We need to have somebody who wants to take the energy that's produced, whether it's electrical, biogas, whether it's cleanup and use as renewable natural gas. We need an off-taker. We need a place to put our digestate. So that typically means land application. Like, who wants the NPK? You know, there are some places where there are so many livestock farms that they don't have enough land to effectively use all the NPK they have available. They have to truck this a large distance. The fourth and the most critical practically is we need some community acceptance. That's where people legitimately have concerns. Is this thing going to smell bad? Well, if you do it badly, yes, it certainly can. But do you need to do it badly? No, there's no reason why these should be done badly anymore. Digesters, it's not a technical risk, right? The technical issues have been solved. We know how to make a digester facility that doesn't smell bad. We know how to make a tank that doesn't leak odors and methane. That's well understood. We know how to make an internal combustion engine that's reliable, right? We've been doing that for a long time. Things are all well-established, proven technologies. And we're just putting them together in new and interesting ways, to deal with the waste, conserve the NPK, produce energy as well.
Yes, it's a very So can you take us through one of your very exciting project you're working on or have done? There must be a lot of exciting projects, no?
There are a lot of projects. Now, unfortunately, our most exciting ones are still confidential because of our small size. We're not conflicted to large manufacturers of equipment or systems. So we get involved in some 8-figure disputes where a project went sideways in the past. But we can speak to those kinds of issues in general. The specific case we're working on is an excellent opportunity. So there's a very enterprising farmer in the United States who is looking at how to pair the digester that he has on his farm with his livestock and pair that with the amount of land he requires and understand how many miles or kilometers radius he needs to go for food and trucking costs, build the business model that is scalable. At the end of the day, we have a above ground bolted steel tank, right? Pretty much the simplest thing ever from an engineering perspective. Once you have one design, if you make 2 or 100 of these, it really doesn't matter. You have great economies of scale. If we can tag 200 milking head of cattle, a fair size family farm with 4,000 cubic meter digester storage tanks themselves, and then add 10 or 20 or 30,000 tons per year of food waste at somewhere between $50 and $100 per ton of tipping fee. That's how the model starts to build out. In electrical case, you would probably have a 1.5 megawatt scale of production off of that. And all the NPK is conserved, and that material can go back out onto the farm fields. We had some questions about the fuel value of the manure. Surely this has been studied a lot of times from textbooks from 20 years ago. We have 3 numbers from 3 different textbooks, wildly varying. A local party take some samples, and those are different still by double what was in the textbook. And we had a second consultant come out and take a sample, and it was half of the previous value. We have so many numbers, we don't know what to trust, and ended up calling us and myself and my colleague, Dr. Michael Nelson. We went to the site. From our experience, we could tell what had happened. But in the farming practices, the cattle, they would stand on a concrete pad. If you scrape that concrete pad, you would get one quality of manure. If you scraped outside where the dung had been sitting in the sun, maybe the dung had been sitting for 10 days in the sun, it was pretty much dirt with no fuel value left. Understanding the sample context was very critical. So doing one sample in the summer and one sample in the winter, dramatically different fuel value. We had them scrape the pens clean and come back 24 hours later. They would come with the big bulldozer blade and push, and would have this wave of manure, which would have been 5 meters wide, maybe, and about 1 meter tall at the front of this blade, but it was all less than 24 hours old. And we're able to then sample that, do a statistical approach to sampling that to get some valid numbers. And we said, okay, this fresh manure, less than 24 hours old, consistently all year long will have this quality of gas. And the stuff that's been out baking in the sun for 6 months, that's just dirt. There's no fuel left there.
Okay, so with all this knowledge, all these technologies that's happening, and thank you, I learned quite a bit about this tech. If a wannabe entrepreneur who wants to go in the industry, someone who grew up in the farm, understand the stewardship, saying, okay, I want to do something for the community, where does he or she start? Or what's your advice for him or her?
So the number one is people, right? This is a people business. Like I mentioned, the key things you need is you need to secure feedstock supply. That means you need to have good, strong relationships with the people who own and manage your local food factories, the people who manage the restaurants who have the French fry oil. You need to have good relationships there so you can have guaranteed feedstock supply. That's critical. On the other side, you need to have good, strong relationships with your local farmers, because these are the people who will have enough hectares of land and grow enough crops, whether it's hay or maize or whatever, that you have a permanent outlet for your digestate. You need to have the inlet feedstock, you need to have the outlet digestate. So the people who can develop those two strong relationships can be the bridge. The business developers and entrepreneurs, they're the bridges, bridging the inlet to the outlet. And then the third bridge is to the off-takers, the folks who are interested in purchasing your energy, your natural gas or electricity. What do they need? When do they need it? How much do they need? And then the fourth bridge has to be to the community, because we know that these systems should work well. They're engineered well. They don't smell. That's not an issue. But in the past, some have. There's a little bit of that reputation that you need to have a strong relationship, build some trust with the community. Well, I can point to 10 examples that are close to communities and don't smell at all and don't have odor complaints. But everyone else can probably point to 10 facilities that were designed poorly, operated poorly, and smell terrible. Both are factual. So how do we know that you're going to build your system and manage your system a way not to cut costs that might result in some oversight that smells bad, but you're going to take good care of this as a piece of our community for the long term? So it's those four bridges that the entrepreneurs need to put together: feedstock, digestate, power off-taking, and the community. If you can make that diamond shape, all those four corners together, then I think you really got something.
Wonderful. What else you do for fun? You are very big into this topic. Anything else you want to do in a personal life, or anything else I could have asked you want to share?
I'm happily a father of three strapping sons who are just launching themselves into their university careers at this point. So my wife and I were empty nesters now for 2 months, which is a very strange situation at home. So there's ourselves, our dog, but the house is pretty big when the kids are all off at university. So we've been traveling some as well. I was in Africa, in Europe, in Ireland in the past little while. So I would love to actually come to your neck of the woods, whether it's the Philippines, Manila, down into Australia, South Asia, all of these places. I've never been. I've worked Europe and Africa. I've worked in North America, worked across South America. This is one piece of the world I've never been to. So this would be my goal in my personal life for sure.
Interesting, because I have worked Australia and all over Asia, except 1 or 2 countries, and not Africa or Europe I've just visited. So it's interesting. Our two worlds are very different.
It is. My colleague Trisha, who you may see her on our YouTube channel, she does a lot of work with our training and educational work that we're doing. She's originally from the Philippines and moved to Canada when she was 11 years old and has a lot of family there and looks to go back. So certainly that's on the list as well. We'll be making the right business trips all around that part of the world for sure coming up.
So thank you very much, David, for your time. I hope this was useful.
It was very interesting. I enjoyed it tremendously, and hopefully we can talk again sometime.
Thank you. We hope you enjoyed this episode of Energypreneurs. To continue listening to this conversation, please visit us at Energypreneurs. Thank you. See you next time.